Okay, so hello everybody. We've been looking at solving the Laplace equation using the method of separation of variables. And so in this lecture, we will look at an illustrative and interesting example where we apply the methods that we have already developed and uh, show you in detail how it works out in practice. Okay, so let's look at a steady state temperature distribution problem, right? I mean, it's really the Laplace equation. So we have developed it in a sort of more abstract formulation, and it's applicable to solving for the potential in an electrostatic problem, but it's also equally well applicable to find the steady state temperature distribution. So imagine this uh, semi-infinite rectangular plate, right? So the top and bottom are maintained at 0 temperatures of this rectangular plate, so it lies in the xy plane. So it has this width is a, and so the left end is maintained at some temperature T0. So the question is, if this entire system reaches steady state, what would be the temperature at all the points on this semi-infinite rectangular plane? So the way to solve this is to basically solve for the Laplace equation, right? So the Laplace equation is dou squared t by dou x squared plus dou squared t by dou y squared equal to 0, and we proceed with the standard method of separation of variables. So let's quickly write down the boundary conditions involved. So the boundary conditions involved here are t of when x equal to 0 and for any value of y, so it has to be t0, that's the left end. Well, I mean, any value of y less than a, y is assumed to be restricted to the region 0 to a, and t of x comma 0 is 0, that's the bottom end, and t of x comma a equal to 0, that's the top end. But so in addition to these three boundary conditions, there is also one more boundary condition which comes from it's a physics physically motivated boundary condition, right? So that's this one, which is basically for large x, this temperature must die down, right? So there is no way to sustain some some finite temperature as you go far away, because all you're doing is maintaining this end at t0. So for t of x comma y, as x tends to infinity, in this region, it must die down to 0. Now this is once we have these four boundary conditions explicitly written down, we see that this is really a Dirichlet problem, right? So it's like the boundary conditions are specified on all the boundaries. I mean, you have a closed interior for which you want to solve the Laplace equation, and so indeed there is a solution, and that is a unique solution, right? So there is a uniqueness theorem which we didn't go into the details of, but really, if you can find a solution that's going to be unique, and so the way to do this is the technique is the separation of variables, and we make this on sorts. We look for solutions of this very special form, t of x comma y is equal to x of x times y of y, and then we will see that there is a way to stitch together solutions of this kind to match your boundary conditions. And if you are able to find one solution which satisfies the Laplace equation and also satisfies the Dirichlet boundary conditions, then you are guaranteed that that is the solution. So that's where the power of this method comes from. So we'll recall, right, that if you have we could choose exponentials or sinusoids, right? So in this case, we want our solution to die down to 0 for a large x, and so it's actually it's appropriate in this context for capital X of x to take on exponentials and capital Y to take sinusoids and cosines, because after all, at the bottom end and at the top end, it has to go to 0, right? So it's appropriate to choose sine of py and cosine of py for y, the function y, and x is going to be exponentials. Furthermore, since t of x comma 0 is given to be 0, the cosine functions cannot appear. So it's in fact only the sines which will appear, and also these p's themselves are restricted, right? So this is like we described in the more sort of general discussion we had. So P must be in fact be chosen to be such that sine of PA must be equal to 0, right? So that is this boundary condition, and therefore P must be chosen to be n times pi over A, where n takes values 1, 2, 3, so on in positive integer values. I mean, there is an overall constant that you will anyway you're allowed to put in, and so therefore you don't have to consider the negative value. So we have n taking all positive values, and only exponentials of the type e to the minus px will count. So e to the plus px is going to blow up at plus infinity, which is unphysical. Therefore we need to work with only exponentials of this kind, e to the minus px. And so the temperature distribution is then seen to be expressible in this infinite series, right? So summation over n equal to 1, there are these coefficients which need to be determined, right? So there is still a boundary condition that we must plug in, alpha n times e to the minus n pi x by a. So that's where the constraint on p is put in, then sine of n pi by a times y. So this is the infinite series representation for t of x comma y, and there is still alpha n which need to be determined. And to do this, we bring in the final boundary condition, which is actually the first boundary condition here, which is t of 0 comma y is equal to t naught. So the left end is maintained at t naught. So t naught must be equal to, when you put x equal to 0, you have alpha n times sine of n pi y by a. So this can immediately be worked out using Fourier's trick. So you just multiply on both sides with the appropriate sign of n pi y by a if you are interested in extracting this coefficient alpha n. This is the standard technique. So you can check this and convince yourself that indeed this will extract for you alpha n, right? So all the other signs corresponding to other terms will go away when you do this integral. Only one of them will survive, and then the factors are appropriately put in. You can check it, and then this integral itself is straightforward to work out, and you will get 0 whenever n is even, and you get this answer 4 times t naught divided by n pi. So that will be a factor of a which will cancel with this a, and you will just get 4 times t naught divided by n pi if n is odd. So basically it falls off with n as 1 over n, and then there is this factor 4 t naught by pi. So the full solution can be written down. Now we have the full answer now, basically t of x comma y is equal to 4 t naught divided by pi, summation over only odd values of n, 1 over n e to the minus n pi x by a sine of n pi y by a. It's a fairly straightforward problem, and there is this infinite series solution. So what makes this problem particularly interesting is that in fact there is a closed form expression available, right? So there is a very nice final answer which we can write down if we do a little more work, and that in fact connects back to our study of complex variables. So the way to work out this infinite series is to look at this quantity z. So you have sine of n pi y by a. So whenever you have a series in sines, it's convenient to also consider the same series with cosines instead of sines, and then take cosine, the term involving cosines, plus I times the term involving sine, and then you conveniently write down cos theta plus I sin theta as e to the I theta, and then you will have these exponentials. So I will allow you to check this. So if you introduce this variable z is equal to e to the minus pi by a times x minus iy, we can rewrite this infinite series as actually nothing but t of x comma y is equal to 4 t naught by pi times imaginary part of this simpler looking infinite series. So there's only the odd numbers appear here, n equal to 1, 3 and so on. Therefore this series is then seen to be actually a combination of log of 1 plus z and log of 1 minus z. So the even terms have to be cancelled out, and then you have to take this factor of 2. So again I will allow you to check this. So it's imaginary part of log of 1 plus z minus log of 1 minus z, the whole thing divided by 2, and then this is nothing but you get a 2 t naught divided by pi, imaginary part of log of 1 plus z divided by 1 minus z. So I will allow you to do some simplifications, and then we have this final remarkable exact result, which is t of x comma y is equal to 2 t naught divided by pi tan inverse of sine of pi y by a divided by hyperbolic sine of pi x by a. So it's a very nice cute result. which comes about, and it's a rare phenomenon that this kind of a method of variable separation of variables will yield for you a closed form solution. And also in this form, it is straightforward to directly plug this into the original PDE, the Laplace equation, and check that indeed it satisfies the Laplace equation. Also, it's straightforward to check that indeed all the boundary conditions hold. So because there is a uniqueness theorem, indeed this is the solution. Okay, that's all for this lecture. Thank you.